Good morning, everyone, and welcome to our Minnesota Stormwater Research Spotlights, part of the Minnesota Stormwater Seminar Series. My name is John Bilotta, and I'll be your moderator today. We are pleased to have so many of you with us. We see many of you still rolling in the room here. I did want to just mention, we were looking at our participants today. We have a vast majority of participants from Minnesota, but we even have an international audience joining us, people from at least 2 different countries. So welcome, everyone. The Minnesota Stormwater Research Spotlights are highlighting projects funded through the Minnesota Stormwater Research Council. Alternating on the opposite months, we bring you the Minnesota Stormwater Seminar Series, bringing national experts coupled with a panel to discuss advanced stormwater innovation and knowledge and see where we can apply that to our communities here in Minnesota and across the country. You can learn more about our seminars on the website for additional information. As a reminder, all of our past seminars are available on the St. Anthony Falls YouTube channel. You can visit the website and find those past recordings and review them, listen to them for your pleasure and to remind yourself of some of the great information that we heard over the last couple of years. A reminder that you can find out more about the project that you're about to hear about today, but also all of our completed research projects and our ongoing research projects by accessing the Minnesota Stormwater Research Council website. And if you look down on the webpage, you can see 2 hot links to either current projects or completed projects. You can access those to find information about any individual project. I also want to mention that we're in our final months of our capital campaign to pool together research funds for our next competitive research cycle in 2022. And so the Minnesota Stormwater Research Council is looking to pool together $175,000 that we can invest in other urban stormwater research projects in 2022. We use that money to leverage and to couple that with our funding that we get from the Minnesota Clean Water Land and Legacy Amendment, and also funds that we contribute through the Water Resources Center. So if we've not heard from you or your organization about your contribution to the research pool for this year, please do contact me for more information. Also, I'd just like to let you all know that we will have our final seminar for 2021 on December 16th. We will welcome a close colleague of many of ours, Michael Dietz, from Connecticut Sea Grant and from the Connecticut CLEAR, which is the Center for Land Education and Research. We've done a lot of collaborative work with Mike and his colleagues over the years with Connecticut, most notably for the NEMO program that we brought over to Minnesota about 2 decades ago. And also let you know, we're going to continue the Stormwater Seminar Series throughout 2022. Watch for our schedule to be announced to that in the first week of December. So a little bit about logistics today before I introduce our guest presenter. Please use the Q&A function of Zoom to ask your questions to our presenter today, not the chat box. If you have technical difficulties or need to reach me or my co-host, Andy Erickson, please put those in the chat box. But otherwise, please put your questions to our guest presenter in the Q&A panel. And you can ask those questions anytime during the presentation today. So with no further ado, I'd like to welcome our guest presenter today. The topic that he's going to talk about, the research project that he's going to feature, was funded as part of our 2018 research cycle with the Minnesota Stormwater Research Council. And with the completion of his project today, we have really reached a milestone. Completing 15 of the 23 projects that we've invested in since 2016. And so I really encourage you to not only check out Greg's project today, but all the other projects that have been completed in the recent months. So with that, I'd like to introduce our presenter today, Greg Wilson from Barr Engineering. Greg brings a vast amount of experience and has worked with many of us that are participating in our seminar today. He brings over 31 years of experience working in water quality, urban water management, and TMDL implementation and construction. The project that he's going to be talking to us about today is looking at urban stormwater ponds and the application of spent lime to control phosphorus release from the sediments. And if many of you are probably aware, we've done a lot of research looking at our urban stormwater ponds in Minnesota and across the country, and they are not always performing as they were designed and as we intend them to do, and dissolved phosphorus is one of those issues. And so we invested in a project that Greg has led, and we're anxious to hear about his results after 3 years of study. So with no further ado, I want to turn things over to Greg Wilson and give him a virtual warm welcome. Take it away, Greg.
Good morning, everyone. Really appreciate the opportunity to follow up on the results of this study. And as John described, its importance is that we've found in some circumstances that it's not always widespread maybe, but there certainly are many times where we're not getting the water quality treatment that we desire from some of our stormwater treatment ponds for phosphorus removal, due to the fact that at least in the summer anyway, some of these ponds are stratifying, they're going anoxic, and then we get some release from the sediments that really can affect the overall treatment efficiency of these ponds. So before I get into it in too much detail here, I just did want to acknowledge that this project was supported by the Minnesota Stormwater Research and Technology Transfer Program administered by the Water Resources Center, and we included appropriations through the Clean Water Fund and via the Clean Water Land and Legacy Amendment, and from the Stormwater Research Council. And so really appreciate the grant funding that we received for this as a byproduct of our work on the project. We also got quite a bit of in-kind contributions from our project partners. First, want to acknowledge the co-investigators that I had from our office here at Barr, Keith Pilgrim, Kevin Menken, Aaron Anderson-Wentz, and Tyler Olson. And then we've got a list of partners that helped us with a number of different things, including helping to identify ponds that we could actually try this concept out at the field scale level. That includes both the Vadnais Lake area, WMO, and the Ramsey Washington Metro Watershed District. We were able to, because of spent lime that was available both through the St. Paul Regional Water Services and the city of White Bear Lake, we were able to get assistance from each of those folks for our lab work, as well as ultimately the White Bear Lake source of spent lime slurry was used for the field applications. And the two ponds, one in the city of Maplewood and one in the city of Lino Lakes. And we also had some outreach efforts from each of those respective cities, and quite a bit of assistance in helping to get lined up for the field application of spent lime in each of the respective cities. And then the Minnesota Pollution Control Agency granted us a permit, an experimental permit to provide the field application of spent lime. And so really appreciate all the contributions and these in-kind contributions that really, without that, I'm not sure we could have done this study the way we have. So with that, a little bit more background on what our goals and objectives were. In the end, it's one primary goal, really looking at trying to evaluate whether beneficial reuse of spent lime could potentially reduce the sediment phosphorus release from these stormwater ponds. If that works, we may also be able to consider how that might work for lakes. In today's world, the way we are addressing this source of phosphorus is many times we're using alum treatments, aerial applications of alum, and maybe some other buffering agent that would allow us to control pH levels during these treatments. And that there are other experimental methods that are also being considered for controlling sediment phosphorus release in ponds. So our primary objective here was to look at, can we apply spent lime, and will it control sediment phosphorus release from ponds? We started with lab dosing experiments. We weren't really sure how much of this we might need to apply. We know it has worked in the past in some of our previous lab work from the 1990s, actually. But then we also wanted to take it out into the field, apply it to a couple ponds, one Ash Street Pond being in the Blamo watershed and Wakefield Pond being in the Ramsey, Washington watershed. And then follow that up with monitoring to evaluate just how well we think the sediment phosphorus release was being controlled by the application of the spent lime. And then finally, one other significant objective I had with the project was just to further provide a proof of concept that, you know, we've got methods that we think are feasible for applying this spent lime to ponds at a cost, you know, that will also be cost effective and can meet any permit conditions that might come into play depending on how everything went. So we really, I think without the field application of and taking this out to a field scale, I'm not sure. So we got some lessons learned from that. And I think without that, it would have been hard to assess whether or not it made sense just based on lab work alone. So what is spent lime? Well, it's actually comes in many different forms, depending on the facility you're talking about. There are several water utilities around the state using lime softening, and usually a byproduct, an outcome of doing lime softening is that you get what's referred to as spent lime. So the residual after the water treatment process for lime softening results in some form of spent lime. And in the picture on the left, this is ultimately what the St. Paul Regional Water Services produces. It's a very watered down mixture when it first leaves the clarifier, but then they run it through a filter press. And then ultimately right now, what they're doing is spending about $350 per truckload for this filter cake that you see on the left. And they are their capacity, they're producing about 10,000 gallons of spent lime every day. And so that over the course of a year, that's about $1 million to truck this filter cake out to agricultural fields where it today is being used as a soil amendment. It would be beneficial in some cases if you needed pH adjustments in your soils. And so that does come with a cost. The water treatment residual has a cost to it in terms of its disposal or some other reuse that would come into play. In the bottom right, I have a picture of the spent lime slurry that is discharged, comes out of the city of White Bear Lake treatment facility. And then actually they truck it over to the St. Paul Regional Water Services, and then it goes through the filter press like the rest of the material from the St. Paul facility. So, but there's many different forms of spent lime that are being produced for these water softening treatment residuals. I mentioned before in the 1990s, we had done some work just in this here again was lab work where each graph is intended to show just two results. We had several dosages of spent lime that were applied to sediment cores collected, in this case from Goose Lake in White Bear Lake. And the graph on the left shows just how much sediment phosphorus is released without any spent lime applied to it. Just about 6.5 milligrams of phosphorus per square meter per day is what our lab experiments showed when this sediment core was exposed to anoxic conditions. The graph on the right shows that just 25% of the estimated dose that we thought we needed to apply back then was enough to control sediment phosphorus release in the lab. And and the results like these are available for 3 different lakes that are in the Venice Lakes area, WMO, and the results are almost consistent throughout. Just any amount of sediment or spent lime that was applied to the sediment cores resulted in little or no phosphorus release after we subjected it to the lab experiments that were done at that time. What we weren't sure about, though, when we started to revisit this more recently, was if this was a byproduct of is it more of a physical barrier to the release of phosphorus from the sediment? And so this again is, I think, a reason why we really in this study wanted to take this to a field scale and make sure that it was working. We do already pretty much know that spent lime is working for stormwater treatment. There is a filtration facility over by Wakefield Lake in Maplewood, and so we monitored inflows and outflows to that filtration facility that's set up there, and it really was, especially initially here, was very good at removing the incoming phosphorus from stormwater runoff. And so we knew that the properties were there to potentially tie up this. And in this case, we're looking at orthophosphate. And so this is that dissolved component of phosphorus that was getting removed by the filtration facility. So I think the combination of this and the early 90s study of the sediment cores were encouraging for us to try this and try to look at more recently how this might work for us in controlling sediment phosphorus release, and then also identified, I think, the other element to the project that we thought needed to be done, which was to take this out to a field scale level and evaluate how it might be working at that scale. So I talked before about how there are different sources of spent lime. If we step back and go before look at the St. Paul Regional Water Services source of spent lime, before it goes through the filter press, it's got very low solids content. As I mentioned, they're producing about 10,000 gallons per day of the material you see on the left. It's only about 5% solids, whereas the picture that I showed previously on the right here, it is more than double that. And it has a little more solids content, and actually is consistent with material that is more consistent, I guess, with material that you would tend to see folks using for hydroseeding operations. And so this was a source of, or provided an idea for us about which source of spent lime we might want to use for the field scale applications. And so I just want to point that out in advance here. And so actually this was 2 years ago that we started to do the sediment core and spent lime lab experiment work. We had collected sediment cores previously from each of the ponds that we were studying. And so we had the results of that, but we wanted to collect new cores and then in the lab composite that the sediment material with the spent lime. In our case, we were looking at the St. Paul Regional Water Services spent lime, and then comparing that to, and it's very comparable to the water content that's in the sediment as well for both the source of the lime slurry and the individual ponds that we were looking at. Oakmill Pond was a pond that we intended to apply the spent lime to, and so we had collected sediment cores from there. And then, like I said, this was done in 2019. This work was done to test this and look at phosphorus fractions attached to the sediment material with and without the spent lime mixtures added in it. So we tried various doses and then retested them after 1 week to look at how much phosphorus, how the phosphorus fractions had changed with and without the spent lime additions. And so this was done in our lab. like I said, a couple of years ago. Last year was kind of a lost year for us due to the pandemic, and it really wasn't until the beginning of this year that we started to do the field applications. So this is kind of results that we've reported on before. Looking at, we had two primary interests here. We wanted to look at just how the various fractions of phosphorus in sediment, attached to sediment, to the various fractions of sediment, how that varied with various doses of spent lime applied. And so each graph here, we've got two separate cores. Two graphs across the top are at one site, and the graphs across the bottom are at a separate site. Each site, the sediment cores collected from each site were subject to both aerobic and anaerobic conditions in the lab. And then we retested, we have a control in each situation that's shown on the left side of each graph. And then we added varying doses of spent lime to each source of sediment, and then retested to see how the various fractions of phosphorus changed. And what we tend to see is after you get out to the 3 higher levels of dosing that we applied to this experiment, we do start to see that calcium phosphate is showing up at higher levels with the higher dosages, while there's usually a reduction in the organic fraction of phosphorus. The results were very similar, both under anaerobic conditions, as they were very similar between aerobic and anaerobic conditions for each source of sediment. This was also done on the other pond that we collected sediment cores. The results are pretty similar throughout, and it's just a matter of trying to get enough spent lime in the dose here to try to start to see and provide an environment where we can get the formation of calcium phosphate. And that's the hope. It's the calcium carbonate in the spent lime that we want to use to ultimately tie up the phosphate that would otherwise get released to the pond. And so the one thing about these graphs is it does not correct for the mass of the spent lime that's added to each of these. So we realize that there probably is an element to how this might work that's really going to be dependent on the speed with which this reaction might occur, where you are converting the iron bound phosphorus, which is more loosely sorbed, or for that matter, the organic fractions of phosphorus in the sediment, and getting that tied up into the calcium phosphate elements. It may take more time than what we had used in the lab here, which was 1 week. And so, but this provided for us an idea of what we might want to apply. In the end, I was shooting for a dose in the field applications that was somewhere in the middle of the graph here, maybe not as high as the 4.36 that you see in each case, but something closer to that level. And so as a midpoint, with the thinking being that that would be a low enough dose where if there was going to be sediment phosphorus release, we would see it. We would potentially see that, but yet it wouldn't be so much spent lime that we'd be applying that it would start to affect the cost effectiveness. And so this was information that we used to try to extrapolate to the field scale how we were going to do that field application to each pond. The one big consideration we also had to take into account, which our lab work helped with, was just to see too how each of these respective dosages might change pH in the pond. And so the spent lime has more of a basic character to it. We knew it would probably increase the pH, and the lab work confirmed that. What you do tend to see when we applied at least the highest dose to the sediment cores in the lab, we would get pH levels that would exceed 9, which in Minnesota is the high end of the standard for pH and surface water bodies. So we also thought this was important to look at these results to get us an idea to levels that we didn't want to go above, didn't want to have this result in a problem in the field applications. And so it gave us some sense for the sensitivity of how the lab water was changing in relation to varying doses of spent lime. So this became something that we paid attention to closely in the field. What you see on the top left, and what I've really just trying to show a time lapse, I guess. And then the top left, where what we ultimately did was we had a hydroseeding operation, obtain the spent lime from the City of White Bear Lake treatment facility, their residuals from there. In the bottom left, this is almost right after the application started. The pond, this is Wakefield Pond in Maplewood, where the water was very dark, very dark brown, almost blackish in a way. You couldn't hardly see into it at the beginning of the application. This occurred in the middle of June of this year. And but so we're really trying to demonstrate the capacity of spent lime to control sediment phosphorus release in the summer. And so the application was done as early as we could this spring. But we also wanted to try to apply enough, get close to the dose that I talked about from our lab work. And then in the course of doing this, we were continuously monitoring the pH levels in the pond. And then, like I said, from a time lapse perspective, the pond in the bottom left, picture in the bottom left kind of shows what the pond looked like at the beginning. The application was occurring. It probably didn't take more than 45 minutes to an hour to apply, in our case, about 2,500 gallons of spent lime on this date. What you do see is there's a little bit of overspray. You'll get a white residue that will land on the vegetation. But then after the next storm event, that gets washed into the pond. And so these first three pictures are really showing how things look almost immediately after the application. The picture here on the second from right is showing how the pond started to change about 6 hours later. And the transparency immediately started to increase after that. And the following day, about 30 hours later, you could pretty much see right to the bottom of this pond, which is about 8 feet deep. And so we thought that was pretty notable about this. We didn't really necessarily expect it, that it would clear up this much. We're used to seeing this with alum applications, but didn't really know what to expect with spent lime. The one other thing that's notable about this is, as you can see, there's a white residue on anything that's in the pond, whether it's debris or other branches in our case. And ultimately, we ended up with about 1 to 2 centimeter coverage of the sediments in this pond based on the dose that we applied. And it stuck to where it was sprayed. Following the spray, we think it might actually have been forming some flock to precipitate out some of the phosphorus that was already in the pond, some of the solids that are already in the pond, and then would settle to the bottom. And it pretty much, any other time I went out to this pond after that, you could tell that this layer of, and we have sediment core samples taken just actually within the last month that confirmed that there is pretty uniform coverage of the spent lime to this entire pond. This particular pond's about 4/10 of an acre in size. And but it worked out well. It did not take very long to do. And we thought it was the way that it worked for us demonstrated that it should be feasible and effective, at least initially anyway. So what we did then, the first application, I'm going to go through a very detailed table where what we're doing is we're looking at how Wakefield Pond, in this case, the 0 to 2 meter surface of the pond, how the water quality changed throughout time, both in response to spent lime that was applied. So the right half of this table is showing incremental changes. In this case, 2,500 gallons of spent lime was applied between June 3rd and June 17th. And then the change in orthophosphorus and the change in total phosphorus is shown. I've got the raw data for each of those measures here. And then we are also showing data for TSS and chlorophyll, as well as chloride measurements, which just happen to be taken for this pond. And then our partner was also collecting dissolved oxygen levels throughout the depth of the pond, throughout the profile of the pond. And so we've got bottom water dissolved oxygen levels. I talked before about how anoxic conditions, usually at the sediment water interface of these ponds, is what's contributing to the sediment phosphorus release. And so we're really trying to track just about anything that could change the mass of phosphorus in the pond from one time increment to the next. And so then that's really what the right half of the table is trying to do, is to show how orthophosphorus changed during each time increment, how total phosphorus changed, and then what was going on between them or at the individual date. And so in this case, we know that we could see that there's a slight increase in total phosphorus on July 8th. This was kind of between two applications of spent lime, and it corresponded with a time where bottom water oxygen levels were lower. However, there was almost 2 inches of rainfall that occurred, and so we would have had stormwater runoff coming into the pond during that time frame. And so we've got a number of different events that we were able to sample this year to try to evaluate how effective this spent lime treatment at this pond was. For me, I'm always a visual person. It benefits me better to look at some of this data in a graphs. And so what you'll see that this graph is, I was afraid that some of our change in phosphorus concentrations was due to the fact that we were getting incoming stormwater flows, and that could affect the phosphorus levels that we saw in the pond. And so what I plotted out here is changes in phosphorus concentration. And so basically the column of data from both the orthophosphate change, the column of showing changes in orthophosphate, and the column showing TP changes was plotted against the incremental rainfall amounts to see if maybe stormwater runoff was really enough to explain the change in phosphorus levels. Now, on the graph here, so any of these points in this graph that are below the red line are showing me that we had changes, that phosphorus was decreasing within the time increments that are shown in the previous tables. And it really was just a couple times where phosphorus actually increased, whether it was total. We had one time increment here where total phosphorus went up at the same time that orthophosphorus went down. That actually corresponds with about a little less than 2 inches of rainfall that occurred during that time frame. And then one other date where both constituents went up from the previous time increment, and that actually corresponded with much higher rainfall amounts during that 2-week time frame. And so in general, it seems like there is a relationship with the rainfall that occurred as you go from the smaller times. And I think the other thing to consider is what we benefited from this study is that we were in enough of a drought condition at the beginning of this summer when this happened, that in the end it's important to note that the pond water level stayed at or below the normal outlet. So we were not losing phosphorus to outlet discharge, because almost this whole, or pretty much the whole time that we monitored, the pond did not come up to a level that would have resulted in a discharge out of the pond. And so I think that was in a roundabout way, that was actually beneficial that this happened during a drought condition, at least at the beginning of the summer, where we had more control on what was coming into and evaluating what was coming into the pond and how the pond concentration changed over time. So we really just got 2 dates where either total or ortho went up. It could have been a result of incoming flows from stormwater. Like I said, just under 2 inches of rainfall occurred within the 2-week time frame there. As it turned out, the one that with the highest change in total phosphorus, at that same time, the total phosphorus went up, the orthophosphorus went down. If you look at our table, what it shows is this just corresponded. It was a couple weeks removed from the original spent lime application. And during that time, what we saw was that chlorophyll was going up. So it appears as though we had some of the orthophosphorus may have been taken up by algae growth, and then but yet there was an increase in total phosphorus. And so it's hard to say how much of this could have been due to sediment phosphorus release because it was anoxic, or how much of it was really a byproduct of incoming stormwater flows, or just even the disturbance from the original spent lime application. What we do see is each time that we did apply spent lime, there was reductions in both total and orthophosphorus that followed that. There was a couple of time frames here in the middle of the summer in August where dissolved oxygen levels were higher than maybe you would expect conditions should be at to result in sediment phosphorus release. And so we just didn't know if maybe there again, we continued to have higher algae levels in the pond. And at the time that some of these samples were collected, it could have been that it was a diurnal fluctuation in dissolved oxygen that was contributing to the higher sediment, to the higher dissolved oxygen near the bottom of the pond. But then there were a couple of events that later in the year where we should have seen some sediment phosphorus release, and yet there were, for the most part, there were negligible changes in phosphorus or actual reductions in phosphate during that time. So coming back to my graph, what you also see on here is what I described before, is that the initial applications of the two different dates that we applied spent lime, there were significant reductions in phosphorus that are associated with each of that. The rest of the data points you could start to see that there's a pattern that as you get more and more stormwater runoff coming into the pond, that could definitely have explained the increased concentrations in the pond. So the other thing that we did do is to collect sediment cores, and I had talked before about how we had analyzed sediment cores before the study was conducted. We knew levels of mobile phosphorus in and here again I'm going to talk about Wakefield Pond, that those mobile phosphorus levels at the surface of that pond were high enough to definitely explain the sediment phosphorus release that we thought we were getting from that pond. But we also had high organic levels of the phosphorus fraction in the sediment. And so these two graphs on the left show how we think the sediment could be characterized before they spent lime treatment. And then we got the top two on the right here are showing how each mobile phosphorus fractions would be different as you work your way down into the sediment depth at each of the two locations that we sampled, and then how organic phosphorus fractions would have changed. And then you actually see that the organic phosphorus fractions, the top, like I talked about before, we think we've had maybe 1 to 2 centimeters of spent lime covering the sediment. So if you look at the photo over here on the left, you can kind of see it. It's that white layer on top. But when we went to sample it, it was kind of mixed in, and we could actually see some biological activity in the sediment, which was encouraging as well, because I think that helps with the process of over some period of time of potentially allowing us to tie up more phosphate in the sediment. The one other thing that could have done for us, which the bottom right graph shows, is that may have changed the character of the sediment at the interface between the pond water and the sediment. And this loss and ignition, these lower levels of that indicate, and they correspond with the graph above it, which is that we think that we're getting lower organic levels at the surface of the sediment following the spent lime application. And that in turn could also change the sediment oxygen demand in the pond, and could also come back to help explain what I was talking about in the table here before, that where we had a couple of timeframes where, this here again in August, there was very little rain, but yet we had higher oxygen levels. And so maybe that could have been supported by the change in oxygen demand that resulted from this application. And so coming back forward to that, I think that was a notable result from our sediment core, kind of before and after treatment results of the sediment coring that we did. Let's see, I think with the time I've got left here, what I want to do is talk more about the proof of concept topics that we intended to address as a part of the study as well. I've got just the table here to show about how much spent lime I wanted to apply. It looked that would have about 20,000 gallons. We wanted to apply to both Wakefield Pond and Ash Street Pond. These are ponds that are both very close to about a ½ acre in size. In the end, I was not able to get more than 3,300 gallons applied to the Wakefield Pond. And that primarily is a byproduct of the fact that as we started to apply, the first time we applied it, the pH started out at about 7, just barely above 7. And by the time that we applied the 2,500 gallons, it had crept up to a pH of 9. So we had to get the contractor to stop applying at that point. Took the rest of our material over to Ash Street, and really there were no limitations on how much spent lime applied over at the Ash Street Pond would affect our, which is shown in this figure down here in the bottom left. We applied 6,100 gallons there. We did see increases in pH there, but nothing close to the pH levels of 9 that we experienced at Wakefield. So really, we could have continued to apply more spent lime at Ash Street, but our schedule just really didn't allow it. As you probably saw in a couple tables back, we went out there 3 different times to apply spent lime, and that took us into the middle of July. And really, at that point, we just wanted to stop applying spent lime, even though we didn't reach the levels we wanted to be at. We thought we needed as much time as possible to try to see how each of the ponds responded to the amount of spent lime that we were able to apply in the early summer of this year. And so ultimately, the only real limitation to applying more spent lime at Ash Street was our schedule for the project. And like I talked about, pH exceedances at Wakefield. We went out there a second time, applied a little more, and it kind of came up from about a pH of 8 to back up to 9 pretty quickly, and so we had to stop applying at that point. But in the end, what we're left with is for the volumes that we applied, the cost for our contractor. When we start thinking about the feasibility of doing this the way we did it, and what it cost, I think it's important to note that for us, it really only cost about 50 cents per gallon of applied chemical. What you see there's a collage of a couple pictures here in the middle bottom that show the truck, the hydroseeding truck at the top of the hill, and there's a little access road that goes down to the pond. We're really we're able to make this work because they have a couple hundred feet of hose that could be brought down to the edge of the pond, and then from there, the truck is able to put enough pressure on the spent lime slurry so that you can actually spray it a couple hundred feet if you need to. And so really, the contractor was able to just stand on the edge of the pond in one location and reach the whole surface of a ½ acre pond. Now, in our original work plan, we had intended to go to Oak Knoll Pond, which is about a 5 acre pond in White Bear Lake. That pond is shown in the bottom right. We weren't able to, we were afraid that we wouldn't be able to make this work and demonstrate the feasibility of. What you can see is it's tough to access the pond. It's completely surrounded by residential housing around the outside that are very small spaces between each house. And so then it would just become a question of how close could we get the truck and still get the hose down to the edge of the pond. But then from there, we're really talking about, if we can only spray out a couple 100 feet on this pond, we would have to, we'd have to be in a situation where we could get right down to the edge. There's maybe 2 or 3 places at best where we could get close enough to do that. And then ultimately, hopefully get full coverage of the pond. But I think the other concern we had at the time was just how much this would cost, and did not think it would fit in within our budget at the time. So we did change to the Ash Street Pond, at least in the Blamo watershed. So, but in general, I suspect that this will work fine. Even if you can get the truck within a couple 100 feet of a pond, you should be able to fully apply the chemical to something on the order of at least a 3-acre pond anyway. It should work, depending on the shape of the pond and like I said, your access to it. And the cost, the 50 cent per gallon application costs are 5 to 10 times lower than what it would normally have cost for us to do an alum treatment of a similar sized water body, depending on the how the alum application would get done, and whether or not the alum needed to be buffered. So that's kind of why there's a range in cost there. So, but in the end, I kind of feel like if spent lime is even 20% as effective as we know alum is, this will still be the cost effectiveness of using spent lime is still going to be comparable, at least to alum, if not better. And it just becomes a question of how well will this work long term. The other thing that we did have to navigate along the way here was just getting the permit from MPCA to in this case it was for experimental purposes to get permitted to apply the spent lime to each of the water bodies. This in the 2 water bodies that we used, it would be the relevancy from doing that is really tied into the MS4 permit. And so whether you're using dredging or whether you're applying spent lime, the soil leaching or soil reference values become important. And MPCA was comparing data that we had on the filter cake or from the lime slurry from our 2 sources. We had data on the various types of chemicals of concern that they would have and how that related to these SRVs or SLVs. And really what we were able to demonstrate from the analyses that we had from the spent lime from our water treatment process was that we really don't think that there would be any contaminants in that residual that would exceed those levels. And now this wouldn't necessarily be true of all sources of spent lime across the state. If source water had arsenic in it or some other contaminant, this may or may not satisfy the interest of MPCA as it relates to comparing it to soil reference or soil leaching values in sediment that they are using right now to assess what needs to be done with dredged materials. The other way that we had to sort of prove that this material would not be toxic is in the past we had compared the aquatic toxicity of our stormwater treated from the spent lime filter device to the untreated stormwater that we had for a sensitive species, a zooplankton species that we used in the study, and really showed that the spent lime material did not produce unwanted toxic effects in the treated stormwater. Really, no adverse impacts compared to the untreated stormwater runoff. If anything, these results are better in that regard, in the same way that they are in comparison to the agency's soil reference and soil leaching values. And so MPCA then did grant us the permit on the experimental basis, and the one condition was that we had to do the continuous pH monitoring. And as I talked about before, when pH at the 1 pond started to approach a pH of 9, as it's crept up there, then we had the contractor stop applying at that point. And then we continue to monitor pH again throughout the rest of the summer at each of our ponds. So I guess bringing this then and was thinking more about the proof of the concept of spent lime, how would it compare to our other options? So I've made reference a little bit to the dredging materials. In the past, that tended to be what folks would do to maintain their stormwater ponds, is they would dredge. It would provide storage increase and might provide a better long-term solution, especially if the surface of your sediment is enriched with phosphate that could otherwise get released in the summer. But the main drawback with that, and the reason why you don't see it as much in the stormwater ponds as you might, is that it can be very expensive to remove that, to dredge material from ponds. We know that, like I talked about before, we know that alum works. It's not alum is good because it's not sensitive to anoxia. We're comfortable with how it works. We know how to dose it, how to buffer it if we need to in smaller water bodies. And the only real limitation on the longevity in these ponds or shallow lakes is just how much more sediment accumulation are we going to get after an alum treatment. So if we are talking about stormwater ponds and you get, especially ponds with high sediment accumulation rates, we're going to get potentially another layer of sediment that could contribute to the sediment phosphorus release in future years. And so it becomes a matter of thinking about, is an investment in an alum treatment worth it for each of these ponds? And so then you consider two more alternatives at the bottom of this table. Iron filings is again, just like spent lime, it's kind of in this experimental phase, really not sure if it's going to be cheap. You would expect it might be cheaper than alum, for example, but then is it sensitive to the redox conditions or anoxia in ponds? It does, what comes with iron filings, it does have a raw material cost, but just like spent lime, we don't really know for sure how well it might work long term. But we do think that just based on this year of monitoring, that we think we can make spent lime cost effective. It is a beneficial, it's a beneficial reuse of a material that would otherwise have to get disposed in another way. And there's always a cost with doing that, with disposing of it. That comes back to what I referenced before, is St. Paul Water Utility, for example, having to spend about $1 million a year to truck the material out to agricultural fields. The one good thing about our lab study with spent lime is we do think it's insensitive to redox conditions. So it'll work probably as well. Similar to alum, it should work as well under anoxic conditions as it does under aerobic conditions in the sediment environment. The big takeaway I've got right now with where we're at on this study is just questions of how long will spent lime work, or is there some way to optimize how we could make it work better long term? And so that kind of leads me to just summarize our conclusions. It isn't totally clear to us if we were able to get calcium phosphate formation. We know that is a slower, it normally is a slower reaction in terms of tying up phosphate, a chemical reaction in terms of tying up and forming metal phosphate, probably much slower than the aluminum phosphate formation that you would get from an alum treatment. But the lab tests demonstrate that we were getting phosphorus partitioning into the calcium, and we just don't know for sure if we could correct our results for the mass of calcium applied. We might be able to differentiate that from a real chemical reaction. But we did see in the lab that it was not sensitive to redox. We do know that we have to mitigate or consider the dose effects in making sure that we don't have pH exceedances in ponds, or if we were to translate this to other larger water bodies, we would definitely want to make sure that we don't have pH increases. We really just see that as being the one place where we could have aquatic toxicity impacts, as if we had pH increases. So then what we concluded from our spent lime applications to the 2 ponds that we made applications in the spring and early summer is that we were very happy with the uniform coverage that we had. It was surprising how quickly it improved transparency after the treatment. Definitely saw that it was removing phosphorus from the water column right away. And then, the post-treatment monitoring showed that there was the potential for release maybe in one event, but then we had other events where we did not see those increases. So like I said, I really just kind of simply say that these results are encouraging. I don't see significant changes in the one time frame that we did have. We started out with a very low phosphorus concentration in advance of that increment. And so really didn't see significant amounts of sediment phosphorus release that we could differentiate from stormwater runoff to the system, at least in Wakefield Pond. And then our sediment core sampling before and after and comparing the results there was that it really did show that the sediment characteristics changed at the surface of the sediment core, which would correspond with the sediment water interface. We think that may have actually a benefit from, at least as it pertains to the sediment oxygen demand that you would otherwise get in some of these really highly enriched systems that really have high phosphorus levels in the sediment. We know that there are pH effects, and we've documented those from the applications that we did. And the methods that we have used, I think my expectation, especially in these smaller water bodies, is that it's going to definitely be cost effective. We were expecting good cost benefit from what we did with these smaller water bodies, and we're happy with how that worked there. Now, if we start to step out to something larger, like I said, a 5-acre pond, we're going to have to think about alternative ways to do that. If in fact we do want to do that. And so that kind of leads me to our recommendations is, we do think that we need more effectiveness monitoring. Obviously, one summer of results maybe isn't enough to go on. We've got one water body where, because of drought conditions, we had a really good handle on the mass balance, we think. But it would be good to try to capture the variability in more ponds or more water bodies in more situations and circumstances that would vary from one place to the next. And then the most important thing I think that we need long-term is just better results of how this works long-term. Like I said before, the costs are much lower than what we would expect to pay for something like an alum treatment. And so even if we had to do more frequent applications of spent lime, it could still be cost effective, but it would help us to have longer term results to confirm that. We'd also like to get, as it relates to variability for these various water bodies, we'd like to get better information on how pH effects differ from one place to the next. We already know, just based on the 2 ponds that we had, that there were significant, that things reacted significantly differently in the 2 water bodies that we looked at. And then we'd like to further develop surrogate measures for how sediment phosphorus release differs in these settings that we're evaluating. And so we think we can further develop that with more effort in the future. We could maybe even supplement our existing lab study to gain a better understanding of what truly is it that could control the sediment phosphorus release. What specifically is it? We don't think we necessarily have a great handle on that right now. And then how that might be sensitive to the various doses that we apply. And so whether it's lab work or more field study or both, we think there's benefit to doing more further study on this, and then continue to just track our costs and feasibility. That would be another advantage to looking at more water bodies and the configurations of these water bodies and the access issues, because I really think that access issues will change the cost effectiveness of this method for controlling sediment phosphorus release. So we'd also be interested in looking at how that changes over time, especially if in reaction to, like I said, the potential changes that we might have to make and the frequency of spent lime that gets applied. And so I think those are my recommendations at this time. We're currently trying to wrap up the development of the final report and may develop a few more conclusions and recommendations based on some final analysis that we're doing here. But for the most part, I think we're at a place where we're happy with the where we are in this interim phase here, I guess, of considering this technology, and are excited to consider further study in the future. And so I guess at this point, I'm ready to take questions that folks may have. You can reach me at this email address or phone number if you did want to talk more about it.
Excellent. Well, thank you, Greg. That's a lot of information to take in. We do have a lot of questions that have rolled in. Maybe you can get a drink of water there. For our participants, we do have a lot of questions. We will not be able to get to all of these, but we do forward all these questions for Greg to answer after the seminar. We'll take about 15 minutes for Q&A here. If you have to drop off, know that this is being recorded too, so you can come back and look at the Q&A after that too. So Greg, lots of questions here, but we'll start with some of the most frequently asked questions. I'll try to do some combination of things, but we'll start with one that's been asked here by a lot of people. Given that phosphorus inputs to the pond would be ongoing, what is the outlook for these treatments to have on substantial impact of phosphorus storage over time? Do you vision multiple treatments per year, every year? How long would these treatments continue? Do you have a crystal ball? I think you talked about some of this in your final recommendations.
Yeah, that is a great question. I think that's maybe one of the fundamental questions that we're still left with. Like I said, we really, the source of funding that we pursued here for this study really just left us with 1 year of the ability to conduct 1 year of monitoring and follow up. And so, yeah, I think what your question really gets at long-term issues that maybe we just don't currently have the answers for. I suspect, though, as it relates to the accumulation of the spent lime material, this, in a way, I do believe we've addressed this through the permit process with MPCA, because we were able to kind of take, whether you looked at the spent lime residuals, the two sources that we had for spent lime, and compared that to the metrics that were of importance to the MPCA. I talked before about those, like the same metrics they would use to consider dredging, for example, and disposal of dredge materials. We know that the material we were using, whether it would have come from St. Paul or whether it came from White Bear Lake, that the pollutants of concern in the spent lime are at lower levels than we would ordinarily see in just about any other pond we've sampled sediment for. And any other pond projects that we've done that involve dredging, where we've had data, and we compare the data for those ponds that, you know, the levels of contaminants that are already in the sediment, the spent lime would just, if anything, dilute those levels. So an accumulation of spent lime, we don't think is going to be, I don't foresee that being an issue. So I guess that's kind of my hedge in responding to this question.
Thanks, Greg. Any thoughts about timing of application? Do you think treating phosphate with spent lime would be, what do you think about fall application during turnover time in these ponds? Any thoughts about that?
Yeah, that could be beneficial. And, you know, maybe that's just another thing to try to address with further study on this topic, would be to just look at that. I think that what you'd probably gain from that is you might remove more of, like we said, like I mentioned before, I think that when we apply the spent lime, we tend to think that maybe what's going on there is that there's some iron in the ponds, especially if there were anoxic. And so by increasing the pH, that we may be contributing to some flock formation of the iron that's in the pond that would then precipitate out the phosphorus and bring that to the bottom of the pond. And so if we think, so it could be that the timing of doing this in a roundabout way could be that it's beneficial to do it when you think you do have phosphorus at the highest levels, and that may actually be in the summer. The one thing I should say too about our other constraints that we found from doing this, and the reason why we didn't get the spent lime applied until June, was there were road restrictions on this. We had a 4,000 gallon capacity in the hydroseeder, and so that's a very heavy, you're transferring a very heavy load. And so you probably can't do that in the spring because of road restrictions. So we could just about eliminate that from consideration. But now whether or not you could do it in the fall or the summer, anytime in the summer or fall, I think that should be fine.
Thanks, Greg. I want to go to a question or two about your graph where you had all your results, lots of data there. A question here about one of the events covered in the data table, specifically, it looks like the 22nd, there was an event that looks like there was a significant increase in orthophosphate, but chlorophyll dropped quite a bit. Are these related? To what extent do you think algae growth in the summer masked or impacted any effects of the treatment?
Yeah, I do. I think that was the reason why I kind of bounced back and forth between the table and the figure here, was we didn't think we could fully explain everything that was going on just based on the incoming stormwater runoff. And let me see if I can find the 922 event here. And so, yeah, I think that, okay, so there was right. We don't know, could it be that there was that algae died off at the later in September, and then that, because the chlorophyll levels went down, but the orthophosphate went up. So could that have been a potential source of orthophosphate? I think that's plausible if I'm understanding the question correctly. So no, I don't know, but earlier than that, I said, if we come back to the earlier part of the summer, I actually think that we had some higher orthophosphate levels, and then we applied the spent lime, it dropped in half. Both the total and orthophosphorus dropped in half, and then it went down after that. And so, yeah, that we could have had algal growth that was contributing to the effectiveness in that regard, but then it didn't really probably change the total. In fact, it looks like the total slightly went back up, but it was going up from a much lower level. So I don't know if I fully answered the question there, John, but there are some dynamics in these ponds that you definitely have to consider. I think the one other thing while I'm looking at this table I forgot to mention is you do see some slight increases in chloride after the treatment happened, which would be another potential concern. Now, when we looked at our filter cake analyses, or for the residual analyses from each of the sources of spent lime, chloride is actually not, it was analyzed, but it was really only detectable in one sample for each source. And I'm not sure if we weren't able to close the loop with the water treatment folks at White Bear Lake yet on this, but I don't know if they're adding ferric chloride at any point during the treatment process. If they are, maybe that could be a source of chloride. So that would be another thing, which I know different municipalities are adding different chemicals in addition to lime as a part of their water treatment. So, but that's a byproduct. That's another parameter to consider and pay attention to, and we'll definitely cover that in our report.
Great. And yeah, that was a question asked too, related to that chloride and trying to explain the changes in those levels. So that tackles another question a little bit farther down the list here. Speaking of pond conditions, algae growth and the such, I'm going to grab a question from down below here, Greg. Any thoughts about, many of our stormwater ponds are covered in duckweed and how that might impact application? Any thoughts on that?
Yeah, so that's a great question. I apologize, with the time I had here, we focused almost entirely on Wakefield Pond. It was a more controlled setting. It didn't have the duckweed. Now the other pond, Ash Street Pond, it was not as controlled of a setting. And so I didn't really focus on that very much for this talk, but it did really have a duckweed component to it. And so we were able to kind of look at that visually. In fact, part of the reason why I didn't rely on the results over at Ash Street Pond as much as I actually was concerned that we were getting duckweed in some of our samples, and then you get some weird results from that having happened. What I would say anecdotally, what I've seen from the applications we made at Ash Street Pond was that there would be duckweed there. We'd apply the spent lime, and it would just kind of displace the duckweed a little bit, but you'd come back out there the next time and there'd still be duckweed. So and the growth of that and the dynamics of duckweed in that pond are probably driven to some degree too by the fact that pond just happens to have some significantly more potential source of stormwater runoff coming into it, and so that could just continue to feed the duckweed there. But if what is driving duckweed growth is the conditions that correspond with lower with higher sediment oxygen demand and more quiescent periods than during quiescent periods, then I think that what I'm encouraged by is just at least the application, if it really is changing the character of the sediment at the sediment water interface, well, maybe then hopefully we should have a positive impact on duckweed growth and reducing that in some of these systems. But that's again that's a great idea for further study.
Thanks, Greg. We'll just take a couple more questions here. I'm going to combine a couple. Do you anticipate, well, two questions here. Do you anticipate if we were to continue applications, some sludge or residue would have to eventually be removed? Would we continue to build up? And related to that, your application wasn't what you had hoped for. You were going to apply more, but you did. It amounted to 2 centimeters. Would that have built up to 6 to 8 to 10 centimeters? And any thoughts about build up, and would we have to do removal?
Yeah, that's a good question. Now, I think in the end, I suspect that full coverage, and at least in the Wakefield Pond setting, might have been on the order of about 1 centimeter. If I were to uniformly look at it, I'm going to quickly go to one of the photos I had here on the bottom left on this slide, and if you guys could still see this. And so it really just kind of shows that what we actually saw were there were worms in the sediment that we think were sort of facilitating some mixing there in the sediment. So yeah, it looks like it's a bigger layer, but I actually think it was mixing in with this sediment. And this sediment naturally was very flocculent in advance of doing this treatment. It was very flocculent, had very high oxygen demand. So no, yeah, but yeah, at some point, if a few extra centimeters on the bottom of the pond starts to cut into maybe the treatment design for any individual pond, then yeah, I could see that someday you would obviously, if you really were going to be doing this quite often, that at some point you would just simply want to do some dredging. But I think our hope is that this may be an alternative way, especially in ponds that are over designed. What we know historically a lot of these ponds are actually stratifying. So if they're stratifying, they're probably already larger than they needed to be. And in many cases, that's a byproduct of the design that, you know, the Bill Walker NERP design called for sediment storage. And so if we already had that going in, it could be that some of these already have more storage in them than we think they really need for settling of pollutants.
Great. Well, thanks, Greg. I'm going to end with one last question. Reminder, everyone, we will give Greg all these questions to respond to after we conclude the seminar today, too. So 2 questions here. I'm going to try to combine. Do you think there's any way to do a mass balance to clarify how spent lime could improve or did improve efficiency or removal efficiency of total phosphorus? And with that, is there any way to put the results, in your opinion, into pounds of phosphorus removed as communities think about, let's say, their TMDL permit or their MS4 permit? So I'll leave it quantifying this.
That's a good question, John. I also see there's one asking about a control pond. And so our challenge with doing these studies really is that we're at the mercy of, you know, like in the same way that we had a drought this last summer, or, you know, a sort of a moderate level of drought in the beginning of the summer. You know, we're sort of at when we do these field scale assessments, we're sort of at the mercy of the climatic conditions that we have happen. And now we can do some monitoring before and after, and we have done that in this case. And so we can kind of compare that, but in the end, we're left with having to sort out what we tried to do, especially at Wakefield Pond, was we think we've got a good handle. We know we've got a good handle on what left the pond, which was nothing. And we think we've got a good handle on what came into the pond. And then we know how the pond water quality changed throughout time. And so, yeah, I mean, I think it just is a matter of how will this differ under more normal climatic conditions where we are getting inflows and outflows, and how does that compare to sort of the before condition? But it almost requires a lot of a really detailed monitoring. And so we would have to spend a lot of our resources on getting good monitoring before and after this, as well as maybe some modeling to supplement those gaps in our understanding as well. So, but I think it can be done. And you know, we in our case, we think we had a good handle on what was happening in Wakefield Pond, at least for this summer. But yet, you know, there are a lot of confounding variables here. And I could see under more normal climatic conditions where this might be tougher to categorize some of the individual sources and sinks.
Well, thank you, Greg. We really appreciate all of your information and sharing the project with us this morning. We look forward to your final report. A reminder that when Greg's final report is available, we will post that on the website under the completed projects of the Minnesota Stormwater Research Council. Please join me in a virtual thank you and applause for Greg and his great work today. With that, I'd like to wrap up our seminar today. A reminder that December 16th, we will have our Minnesota Stormwater Seminar Series featuring Michael Dietz from Connecticut. Please join us for that. Watch for our announcement of the 2022 schedule. And of course, remember that all the presentations are available on the SAFL YouTube channel. My thanks again to Greg. My thanks to our co-host at St. Anthony Falls Lab, Dr. Andy Erickson and Dr. John Gulliver, that makes all this great presentations and our seminar series possible. Thank you to all of you for joining us today as we continue to offer these seminar series. Enjoy your rest of the day. Thank you for joining, and that will conclude today's seminar.